This is Math Applications and Interpretation, Paper 3, Higher Level, November 2022 exam tutorial. So I'm going to go through each problem, and I want to start by directing your attention to the instructions at the top of the page. Make sure you note a couple things. Read the whole paragraph, but one thing in particular to note is that when you take this exam, you should start each question on a new page. So number one goes on one page. It may bleed. It probably will go, take multiple pages. But once you finish that, you need to go to number two and start on a new page. And the second thing to note is that you should show all work as much as possible. If, for example, if graphs were used to find a solution, you should sketch those graphs as a part of your answer. So just want to note those things. And one other thing it doesn't say here, but you should note, is always use the unrounded version of any previous answers to calculate any further answers. Okay, so starting with number one, we are looking at approaches to using historical sports results for making predictions about future sports matches. So two friends, Peter and Helen, are discussing ways to predict the outcomes of international football matches involving Argentina. Peter suggests analyzing historical data to help make predictions. He lists the results of the most recent 240 matches in which Argentina played in chronological order. Then he considered blocks of 4 matches at a time. He counts how many times Argentina has won in each block. The following table shows the results for the 60 blocks of 4 matches. 240 matches divided into 4 blocks size of 4 matches is 240 divided by 4, or 60 blocks. So we should expect that the frequency over here should add up to 60. So in other words, in a block of 4 games, there were 0 times that Argentina won none of those 4. In a block of 4 games, there were 11 times that Argentina won 1 of 4. There were 21 times it won 2 of the 4 games, 21 times it won 3 of the 4 games, and 7 times it won all 4 of the 4 games. So part A asks us to determine the mean number of wins per block of 4 matches in Argentina. This is an expected value question. So we would multiply the frequency times the number of wins and add all of those together. And then divide by the total number of our frequency. So 0 wins had a frequency of 0, plus 1 out of 4 wins had a frequency of 11, plus 2 had a frequency of 21, plus 3 had a frequency of 21, plus 4 had a frequency of 7. All of that should be added together and divided by the total number of blocks, which was 60. And when you do that, you get 2.4. This requires that you get the correct answer, and if you write your work along the way, then if you show what you did to get this work, then you can get credit, a method point, even if you don't quite arrive at the correct answer, and if you make a mistake in your workings. Here, now Peter says he thinks it's a good idea that the data can be modeled by a binomial distribution with n equals 4, and he decides to carry out a chi-squared goodness of fit test. So use Peter's data to write down an estimate for the probability, P, for this binomial model. Well, we know that the expected value, the mean, is 2.4 out of 4 games, and so we just need to use what's the probability of that occurring. 2.4 over 4 is 0.6. And that is the answer for P. That's the probability of the expected value occurring. Okay, so use the binomial model to find the probability that Argentina will win 0 matches in the block of 4. So here we would say, well, Peter's data, we are told that it is a binomial distribution. It's distributed binomially with n equal to 4, and the probability of a win is 0.6. And so we just want to run this probability by using the binomial distribution and then letting n equal 0. So the probability that, oh, I guess I should have used a different letter than P because that's a little confusing. Let's just call it X. So the probability that X is equal to 0. And you just use the probability density function on your graphing calculator with this data, and you get that probability is 0.0256. Remember to leave your answer as 3 significant figures, and there you go. And then the expected frequency of 0 wins, we just take, for this data, out of 60 matches total, we would just take that probability, 0.0256, times the 60 blocks, and that would give us an expected number of 0 wins at 1.54. Notice that they actually had 0 situations in which they had 0 wins from a block. We, out of the 60, according to this data, we would expect that they would have had 1.54 win times, so between 1 and 2 occurrences. And just thinking about what it actually means. Going on to the next page, he sets up this expected frequency table. As some expected frequencies are less than 5, Peter combines rows for his table to produce the following observed frequencies. He then uses his binomial model to find appropriate expected frequencies correct to 1 decimal place. So you can see, essentially, he created this model by doing what you did here, identifying the chance of exactly 0 wins, exactly 1 win, exactly 2 wins out of, and how many times we'd expect that to occur out of 60 games. But they cleverly decided to not give the answer away by setting it up so that the first 0 and 1 had to be combined because of low outcomes. Okay, so Peter uses this table to carry out a chi-squared goodness of fit test, or to test the hypothesis of the data that follows a binomial distribution with n equals 0, n equal 4, 5% significance level. So state the null hypothesis test. So a chi-squared goodness of fit test is asking, is the data, does it have the distribution that I think it does? And so the null hypothesis is that the data has a binomial distribution. That's what we're testing. Data has a binomial distribution and you can include the parameters or the it doesn't have to, I guess n equals 4 is not a parameter, so we'll include that it has a binomial distribution with n equal 4. The number of degrees of freedom, we consider how many categories. We've got 1, 2, 3, 4 categories. We subtract from that the number of parameters in a binomial distribution, and a binomial distribution has only one parameter. A binomial distribution has n comma mu, and mu is the only parameter, so -1, and then always subtract 1 from the end. And so that gives us, it gives us 2 degrees of freedom. And now we state the p-value. This is where we run the chi-squared goodness of fit test. You can use your calculator to do that. You need to have created a matrix with 4 rows and 1 column for the observed frequencies and 4 rows and 1 column for the expected frequencies. And you'll compare those two on the goodness of fit test, and that will give you a p-value of 0.954. And now we're asked to write the conclusion with justification. So we would say, I'm going to come down below this so that I can write it. You need to include your reasons. So we say, since 0.954 is greater than the significance level of 0.05, there's insufficient evidence to reject H naught. To reject the null hypothesis. And it's always a good idea, although this is a sufficient conclusion, but to write what that means. Therefore, we accept the use of Peter's binomial distribution, but you could say something like that too. But I'll leave it at that because IB says this is a sufficient conclusion. That it's sufficient to say it's insufficient, that we had insufficient evidence to reject the null hypothesis. Part B says, using Peter's binomial model, find the probability that Argentina will win at least one of the next 4 international football matches. So we want to know the probability that X is greater than or equal to 1. Another way to calculate this is the probability is 1 minus the probability that X equals 0. In other words, subtracting out the probability of 0 wins. What's the probability of 1 or more wins? And when you do that, you get 0.974. And you might notice that we've already calculated the probability of 0 wins using this binomial distribution, so you could actually just do 1 minus that 0.256 that we already got from part C. Helen thinks a better prediction might be made by considering the transition between matches. To keep the model simple, she decides to use only 2 states, Argentina won A or didn't win B. Helen looks at Peter's list of results and counts the number of times that Argentina won twice in a row, won and then lost, which is AB, lost and then won, which is BA, lost twice in a row, which is BB. Those combinations are represented at the frequency table here. Helen uses relative frequencies to estimate the probability of a transition matrix. Given that Argentina won the previous match, show that Helen's estimate for the probability of Argentina winning the next match is 17/29. When we're calculating probabilities, we put the given on the denominator, and given that they won the previous match, well, that happened 145 times, 85 plus 60. And winning the second match, the following match, happened 85 of those times. So 85 over 145 reduces to 17/29. And we have found that probability. The second part of F asks us to write down the transition matrix T for Helen's model. So hopefully you were thinking as we saw these types of this comparison of values where we're seeing how one event affects the following event, you thought of Markov chains. Markov chains give us probabilities of one event affecting the following. So we are going to create a transition matrix for a Markov chain. And when we do so, we talk about the columns represent our initial state, and the rows represent our following state, next state. So as we set up a structure for this transition matrix, I'm just going to write in that the initial state could either be A or B. And so that entire column starts with A or it starts with B. And the next state is separated by rows. That could be B or B, or B. Sorry, I should have started with A. I don't know why I did that. A is going to be one option represented by the top row, or B is going to be the bottom row. So we will find the probabilities of each of these occurring. And when we do, we already know that AA is 17 over 29. AB would be 60 divided by 145, which reduces to 12 over 29. BA would be 62 out of 94, which reduces to 31 over 47. And BB would be 32 out of 94, which reduces to 16 over 47. And that is our transition matrix T. Part G, part 1, asks, show that the characteristic polynomial of T is 1363 lambda squared minus 1263 lambda minus 100 equals 0. So to find a characteristic polynomial, we need to write lambda minus our first, lambda minus our last, and then take the opposite of the other two terms. Change that. It's going to be the discriminant of that should equal 0. So then, and by the way, you may have written 17 over 29 minus lambda, 16 over 47 minus lambda, and kept those opposite two terms positive. That's fine too. That'll give you the same value. But to find the discriminant of this, we take that product minus that product, which gives us lambda minus 17 over 29 times lambda minus 16 over 47 minus negative 31 over 29 times negative 12 over 47. No, I did that backwards. Negative 31 over 47 minus 12 over 29, or times negative 12 over 29. All that's equal to 0. Here we can see that the two negatives cancel out. So we do have minus. We can distribute. And we've got some pretty ugly fractions here. I'm going to just mention that before. Notice where we're going. We're not too far from our goal here as far as we've now got almost a quadratic. We have a quadratic that's not yet simplified. But notice that we're going to have a bunch of fractions. And what we're trying to get to doesn't. So you might think about what's a common denominator, or what are some numbers, what can we multiply this whole thing by? We can get there in a minute, but I guess we can start by distributing. We get lambda squared minus 17 over 29 lambda minus 16 over 47 lambda plus 272 over 1363 minus 372 over 1363 equals 0. I can, if I want, go ahead and combine like terms here. Oh, oops. With those constants. I could also eventually combine like terms with lambdas, but if you'll notice that I've got a bunch of fractions, I could multiply this whole entire thing by a denominator to cancel out all those denominators, and that would be 47 times 29 or 1363. If I do that, then I'm not going to have to worry about common denominators. So I'm going to try that. 1363 times lambda squared minus 1363 times 17 over 29 gives negative 799 lambda. 1363 times negative 16 over 47 is 464 lambda. And then plus 272 minus 372 equals 0. And when I combine all those like terms, I have 1363 lambda squared minus 1263 lambda minus 100 equals 0. So just a lot of details to pay attention to there, but really we can deal with a lot of it by just multiplying by a common denominator, and we have achieved what we wanted. Part 2, though, says hence or otherwise find the eigenvalues of t. So to find those eigenvalues, we need to solve for lambda. All you have to do here is go to polysimult and use the polynomial equation solver using your coefficients of this lambda expression. And when you do that, you're going to get values. I always encourage you to switch those values over into fractions in case they're decimals. See if you can get a fraction value so it will be more exact. And in fact, you end up with lambda equal to 1 and negative 100 over 1363. Those are the eigenvalues. And part 3 says, then find the corresponding eigenvectors. We do this by taking our matrix with lambda and substituting each of these values of lambda in. So let's see. I'm down here on G, part 3. For lambda equal 1, I've got 1 minus 17 over 29, negative 31 over 47, negative 12 over 29, 1 minus 16 over 47. I take that matrix, I multiply it by the matrix xy and set it equal to 0, 0. And I can multiply these together to get an expression for x and y. By the way, this value is 1 minus 17 is over 29 is 12 over 29. So that gives us, from the top row, 12 over 29 x minus 31 over 47 y equals 0. I can do the same thing for the bottom. I can go ahead and multiply this all the way out, which would give me another equation. Essentially, this is the top row of a new matrix, which would equal 0. But it's going to have the same value, so I can just stick with this and solve for one of the variables. So I will solve here for y, and that gives me y equals 564 over 899 x. Here, to find the eigenvector, I'm going to let x equal some value t. So then y would equal 564 over 899t. And so, for instance, if t equals 1, then that would be the horizontal component, and 564 over 899 would be the vertical component. So this is the vector for lambda equals 1. I need to do the same thing for lambda equals negative 100 over 1363. So negative 100 over 1363 minus 17 over 29. I know that's super ugly. Negative 31 over 47. Negative 12 over 29. Negative 100 over 1363 minus 1647 over 47. Going ahead and simplifying that top left value, I get negative 100 over 1363 minus 17 over 29. You can just type that into your calculator and then convert it to a fraction, and it is negative 31 over 47. Yay! So then we take that, multiply it by xy, which gives us that negative 31 over 47x minus 31 over 47y, did it again, equals 0. Adding y, 31 over 47y to both sides. I get, and then dividing by the reciprocal, I get y equals negative x. So letting x equal t, y would equal negative t. And so my matrix, my eigenvector is 1, negative 1. For lambda equals negative 100 over 1363. You need to include the eigenvalue associated with your found eigenvector, and both of those need to be found. So we have accomplished part G. And finally, for part H, we're told that in her retirement, many years from now, that's key, Helen is planning to travel to 3 consecutive international football matches involving Argentina. Use Helen's model to find the probability that Argentina will win all 3 matches. Okay, so we are going to find the steady state for this transition matrix. So we'll know, because many years from now, we're thinking way, way, way off in the future. So what's the likelihood of a win way, way off in the future? So you can put in, if you want, go back to our original transition matrix, type it into your graphing calculator, and raise it to something like the 50th power, something really, really far in the distance. And when you do that, and you need to write down as much of this process as possible, you might write, for instance, 17 over 29, 12 over 29, 31 over 47, is that it? 16 over 47, oops. Raised to the 50th, and then write down our new matrix. 0.614, 0.614. When you do this, you get repeated values. The probability of winning is independent of the probability of losing for the very far future. And you get P3.386 and 0.386 for the probability of losing, regardless of the first. So very, very, very far in the future, the probability of a win is 0.614. Now, Helen wants to know the probability of winning all 3 matches. So we know the probability of a win is 0.614. That being said, so she's won the first match, we should go back to our original matrix and look at, well, given that she won the first match, what's the probability of winning the second match? That's 17 over 29. And given that she won that second match, what's the probability that she wins the next match? Oops, again, that's 17 over 29. So the probability that she wins all of the matches would be this value, 0.614 times 17 over 29 times 17 over 29. And by the way, if you've got a more accurate value than that 0.614, you should use it here. And that, when you multiply all that together, that gives you 0.211. And that is the probability of winning all 3 matches. Again, the probability of winning the first match really far in the future we got from our steady state matrix. And then the probability of using each following match we got from our transition matrix. And there you have it. In number 2, we'll start by reading the bold paragraph, which gives us some context. Some medical conditions require patients to take medication regularly for long periods of time. In this question, you will explore the concentration of a medicinal drug in the body when the drug is given repeatedly. Once a drug enters the body, it's absorbed into the blood. As the body breaks down the drug over time, the concentration of the drug decreases. Let C of T, measured in milligrams per milliliter, be the concentration of the drug T hours after the drug is given to the patient. The rate at which the drug is broken down is modeled as directly proportional to its concentration, leading to the differential equation dc dt equals negative kc, where k is a positive real number. Initially, D is, the initial concentration is D milligrams per milliliter, where D is greater than 0. For part A, by solving the differential equation, show that C equals dt, d e to the negative kt. 2 things here. We're asked to show that, so we know that we need to show the steps, write out the work, and we're given the answer. We want our answer to look like that, to be in that form, meaning we have to start with something else to arrive there and show our steps. But it tells us how to do this by solving the differential. So that's where we will start. I'm going to write out, we need to move the C to solve the differential to the left side, and the dt to the right side. So we multiplying both sides by dt and dividing both sides by c, we get 1 over c dc equals negative k dt. Integrating both sides, we get the natural log 1 over c. The integral of 1 over c is the natural log of c. The integral of negative k in terms of t is negative kt. And then add a constant. Often we use c as our constant, but since we already have a c here, let's use something else like m. And now we have solved the differential, but we want to show that, meaning we need our answer to look like this answer, so we need to isolate c. We can isolate c by raising both sides, base of e. That leaves c on the left side and e to the negative kt plus m on the right. Using rules of exponents, we can break up e to the negative kt plus m to be e to the negative kt times e to the m. And since e and m are both constants, we can let d equal e to the m. And then we have C equals D e to the negative kt. And we have completed the task given to us by part A. For part B, for the remainder of this question, you will consider a particular drug when it is known that K equals 0.2. The first dose is given at time t equals 0, and it is assumed that before this, no drug is present in the blood. For part B, find the time in hours that this drug reaches 5% of its initial condition. I'm going to go ahead and rewrite my C out to the side, my equation, because it says for the remainder of this question, so I'm just going to write that C equals D e to the negative 0.2 t, just so we can keep that centered, because we'll continue to use that. Okay, now find the time when this drug reaches 5% of its initial concentration. Well, if its initial concentration was D, so D e to the negative 0.2 t, and we want to know the time when that is equal to 5% of D, so we can write it as equals 0.5 D. When you divide both sides by D, the D's disappear, and we're just left with e to the negative 0.2 t equals 0.05. You can use the graph on your graphing calculator to find this intersection of those two functions, but I suggest just using algebra. We want to isolate t, so let's take the natural log of both sides to get that t out of the exponent, and that gives us negative 0.2 t equals the natural log of 0.05. Dividing both sides by negative 0.2, we get t equals 15.0. And that's the answer to part B. Moving on, the drug is to be given every capital T hours in constant doses such that the concentration of the drug is increased by an amount of D milligrams per milliliter. To simplify this model, it's assumed that each time the drug is given, the concentration of the drug in the blood increases instantaneously. We have another show that the concentration of the drug is D, it's this expression, immediately after the third dose is given. So show that means we're going to try to arrive at an answer that looks like this. We're told to do so that the concentration, we're looking for the concentration immediately after the third dose is given. And notice that the variables here are capital T. The drug is given every capital T hours in constant doses. So let's think about how much drug is going to be in the body. So we've got 3 doses, dose 1, dose 2, and dose 3. How long has gone by immediately after the third dose 3 is given? Well, immediately after dose 3 is given, 0 hours have gone by because it's immediately after. But because this is the third dose, it's 1 dose after the second dose. So the second dose has now been in the body for T hours, capital T. And the first dose has now been in the body for 2 complete cycles. So it's been in the body for 2T hours. So now what we could do is write an expression for the concentration of the drug. We know that dose 3 is going to have a concentration of DE to the negative 0.2 times 0 because it's been in the body for 0 hours at this point. Dose 2 is going to now have a concentration of DE to the negative 0.2 times capital T because it's been in the body for capital T hours at this point, and the original dose has now been in the body for 2 T hours. We can notice that we could simplify that to get negative 0.4 T, and we can also factor out a D from each of these. And we can also simplify that. That's going to be e to the 0, which is 1. So I'm going to factor out the D and simplify what's left. E to the 0 power is 1 plus e to the negative 0.2 capital T plus e to the negative 0.4 capital T. And I have arrived at the solution or the expression that I was looking for. So as far as what to show, I encourage you to write out all your thinking. You especially need to show this expression. Thinking about, like writing out your thinking about how long has passed, how long each dose has been in the body can be helpful to show that as well. For the next part, we're told that immediately after the nth dose is given, the concentration of the drug is listed here as follows. Show that this concentration can be expressed as D equals 1 minus e to the negative 0.2 capital T over 1 minus e to the negative 0.2 capital T. I don't know if I said that right, but you can see it written there. So a couple of things to notice. We have let's look at what we're given here, this expression, which is essentially very similar to what we had seen a second ago. But we have our most recent dose is given by, could be expressed as e to the negative 0.2 T to the 0 power. And then this dose, the next dose, or the next most recent dose, e to the negative 0.2 T to the first power, and then e to the negative 0.2 capital T to the second, and then it continues. So we have here a geometric sequence where we're multiplying by a common ratio of negative 0.2 T each time, with an initial value of D. So we know for a geometric sequence, well, I've pasted it here from the formula booklet, which this is, you can see it's SL 1.3, it's in the formula booklet, that our starting value, or UN, in this case, is the initial concentration, D. And our common ratio, R, is e to the negative 0.2 capital T. So given that, we can use this sum of n terms in a geometric sequence to write the concentration of multiple doses of n doses, and we would expect that concentration to be, or I can write it as sum, the sum, Sn, would be D is U1. I'm gonna, since we notice here that this is in the form of 1 minus, I'm going to use the second version, the 1 minus version. So 1 minus our common ratio, e to the negative 0.2 T to the nth power over 1 minus our common ratio, e to the negative 0.2 capital T. We can simplify this by pulling the D out. And again, we're using our model here. What we're trying to get to an expression that looks like that form. So pull the D out front and raise e to the negative 0.2 T to the nth power, which gives us 1 minus e to the negative 0.2 n capital T over 1 minus e to the negative 0.2 capital T. And we've done it once again. The next part of question 2 on the next page, we read, after a patient has been taking this drug for a long time, it is required to keep the concentration within a particular range so that it's both safe and effective. Let Hn be the highest concentration of the drug in the body for the interval n minus 1 capital T, less than or equal to t, less than nt. In other words, between a previous dose and next dose, and let Ln be the lowest concentration of the drug in the body during that same interval. Here we have a graph of what that looks like. You can see the drug concentration is dropping off between doses, leveling out, and then a new dose comes and increases. And so that's what we have here. H infinity is defined as the limit as n approaches infinity of Hn, and L infinity is defined as the limit as n approaches infinity of Ln. Find in terms of d and t an expression for H infinity. So H infinity is going to essentially be that concentration formula, d equals 1 minus e to the negative 0.2 nt over 1 minus e to the negative 0.2 t, where n is approaching infinity. So the only term affected by n, is this one. So let's see what happens to that term. Over to the side, I'm going to write as n approaches infinity, e to the negative 0.2 nt approaches. So let's think about what happens here. The negative exponent on e tells us that as we get a bigger exponent, we're going to get a number closer and closer to 0. And so as n approaches infinity, that's going to take us closer and closer to 0. Another way to think of this is e to the 0.2 nt. So n on bottom means we'd have a really, being infinity on the denominator means we'd have a really, really big denominator, which is essentially 0. So since that term is approaching 0, we could actually say that, I'm just going to, for the sake of time, erase this and put a 0 in its place instead of rewriting it. Essentially, as n approaches infinity, hn approaches this value, or hn equals this value. Let me simplify it. D times 1 over 1 minus e to the negative 0.2 capital T. So notice that now we have an expression for H infinity in terms of D and capital T. Those are the two unknowns that we have written there. So this is the answer for part 1. Part 2 says, well, what is L infinity? So we're going to do the same thing here, but we need to think about the lowest level is not the amount immediately after the that dose was given, the most recent dose, but way down here. So more time has passed. In fact, another t time has passed. So L infinity is the initial amount, 1 minus, I'm sorry, I'm just going to write that as, it's basically H infinity times some more, times the amount that the drug decreases over one additional period of time, so times e to the negative 0.2 t. So essentially we use our common ratio here because an additional amount of time has gone by, but we haven't increased the dose. So this is right before the following dose. So using that, we could rewrite this as, well, this is actually in and of itself fine, or we could rewrite it as e to the negative 0.2 capital T over 1 minus e to the negative 0.2 capital T. And that is L infinity in terms of D and T. Part F says, show that H infinity minus L infinity equals D. So let's just see what happens when we substitute those expressions that we just found in for H and L. So you can see we'd have D times 1 over 1 minus e to the negative 0.2 capital T minus D e to the negative 0.2 t, 1 minus e to the negative 0.2 t. The d's factor out, so I'm just going to, for now, cross them out and move them out here. And notice that we have common denominators. So we're just adding two fractions with common denominators, so we can keep the denominator, 1 minus e to the negative 0.2 t, and subtract the numerators, 1 minus e to the negative 0.2 t. What do you know? So those divide out, and we just have d. So we have indeed shown that H infinity minus L infinity equals d. And part 2 also is a show that problem, and it says show that 5 natural log H infinity over L infinity equals t. So we'll do the same thing, follow the same process of starting with this equation, substituting our expressions in for H and L, and then simplifying. So 5 times the natural log of H is d1 over 1 minus e to the negative 0.2 t over d times e to the negative 0.2 t over 1 minus e to the negative 0.2 t. Obviously the d's cancel. You might notice that again we have the same denominator, but if it's not obvious what you should do from there, I will write out. We've still got 5 natural log. When you're dividing fractions, you multiply by the reciprocal. So 1 over 1 minus e to the negative 0.2 t, sorry, that shouldn't be parentheses, times, and take the reciprocal of the denominator, 1 minus e to the negative 0.2 t over e to the negative 0.2 t. We can cross cancel. That leaves us with 1 over e to the negative 0.2 t, which is 5 natural log. 1 over e to the negative 0.2 t is just e to the positive 0.2 t. So another way we can keep going, because we're still trying to get that this whole thing is equal to capital T. When we have a coefficient of a natural log, we could rewrite that as an exponent. So the natural log of e to the negative to the positive 0.2 t to the 5th power is e to the natural log of the 0.2 times 5 is 1. So e to the t. And the natural log of e to the t is just t. And we finally turn to the last page of problem number 2. It's known that the drug is ineffective if the long-term concentration is less than 0.06 milligrams per milliliter, and it's safe if it never exceeds 0.28 milligrams per milliliter. So, hence, for this drug, find a suitable value for D. So we're thinking about our initial concentration values here. The last part of number 2 on the last page, we read, it is known that this drug is ineffective if the long-term concentration is less than 0.06 milligrams per milliliter, and it is safe if it never exceeds 0.28 milligrams per milliliter. Hence, for this drug, find a suitable value for D and T. So we should notice that less than 0.06, that long-term concentration, that is talking about L infinity. The long-term lowest value we ever want is 0.06, and it never exceeds 0.28, so our long-term highest value is 0.28. And if you notice those two values that they stand for L and H, then you should be good to go on this problem because we already have expressions for L and H. So we're going to equate those expressions with these values, and that will give us a system of equations with unknowns D and T. So 2 equations and 2 unknowns is always solvable. So let's get started doing that. We know that the H infinity equation is 0.28 equals D times 1 over 1 minus e to the negative 0.2t. That's the H. And the L equation is D times e to the negative 0.2t over 1 minus e to the negative 0.2t. We can rearrange both of these to isolate D and then set them equal to each other by dividing both sides by this fraction, which is the same thing as multiplying by the reciprocal. We get 0.28 times 1 minus e to the negative 0.2t is equal to D. And doing the same, dividing by the fraction to isolate D, which is the same as multiplying by the reciprocal, we get 0.06 times the reciprocal of that fraction, 1 minus e to the negative 0.2t over e to the negative 0.2t. And we can now equate, then that's equal to D. So for the sake of time, instead of rewriting this, equating these two expressions, I'm going to just erase that middle and set them equal to each other right here. We can simplify this by dividing both sides by this expression. Hopefully you can see that the expression, we have that same expression on both sides. So 1 divided by 1 minus e to the negative 0.2t divided by 1 minus e to the negative 0.2t. And those cancel, and we are left with 0.28 equals 0.06 times 1 over e to the negative 0.2t. And that negative exponent tells us we can just take its reciprocal. So 0.28 equals 0.06 times e to the positive 0.2t. We can divide both sides by 0.06, and we get 4.67 equals e to the 0.2t. Sorry, we're getting a little crammed. I'll come down here. We would take the natural log of both sides to isolate t. Remember to use the unrounded version of this in your calculator. So the natural log of 4.66666 repeating is 1.54 approximately. Again, I'm only rounding to write it down. Equals 0.2t. I'm dividing that by 0.2. I get t equals 7.70. 3 significant figures. All right, so we have found t. Given the fact that it asks us to find d first, I'm assuming there might be a way that would be even quicker to do that, but this is what I'm using. So now I will take that 0.770 value of t and substitute it back into one of the original expressions. I'll just go with this one, that H that equals 0.28. So 0.28 equals D times 1 over e to the, 1 over 1 minus e to the negative 0.2t, or negative 0.2 times 7.7. And when you evaluate that expression and divide both sides by that expression, you get D equals 0.22, 0.22. So we have achieved our goal. And for H, for the values of D and T found in part G, find the proportion of time for which the concentration of drug is at least 0.06 between the first and second doses. So for H, between the first dose and the second dose, we want to know at what time we reach 0.06 as the drug diminishes. So 0.06 equals the original dose, D of 0.22. By the way, we're going back to our original concentration equation. ED to the E times E to the negative 0.2, negative 0.2T. So now we know that D is 0.22, and so we use E negative 0.2 capital T. And here we want to solve for lowercase t to see at what time this happens. And when you do that, dividing both sides by 0.22, taking the natural log of both sides, dividing both sides by negative 0.2, you discover that T is equal to 6.49. So for the first 6.49 hours, the drug concentration after the first dose is above 0.06. And so for 6.49 hours out of the entire 7.7 hours of capital T, which is what capital T means, the length between doses, that would give us the proportion of time for which the drug is at least 0.06, and that gives us a value of 84.3%. And finally, suggest a reason why the instructions on the label of the drug might use a different value for capital T than found in part G2. We found for G2 that T equals 0.7. In other words, the length of time between doses, is 7.7. In other words, the length of time between doses, it should be 7.7 hours. So why do you think that might not be the instructions that are used? So here they're wanting to know if we are understanding the context of the situation, given the fact that this is drugs and people are having to take these drugs. It might not make sense to take a drug every 7.7 hours. So we could round that to 8 hours, and it might make more sense to take the drug every 8 hours, which would be 3 times a day. That is a sufficient answer. Thinking about the fact maybe that we would reach lower than our desired concentration after the first dose might be another reason that we'd want a shorter time period. So there are multiple correct answers for this, but it's requiring that you're thinking about the context of the problem. And the first one that IB lists as a valid answer is rounding to 8 hours leads to 3 hours a day, or rounding to 8 hours leads to just an easier time to schedule. So I would answer rounding 7.7 to 8 hours is easier for a patient to schedule. doses.